time, this video will focus on sort of an extension of what we looked at with refraction and Snell's law. It's a phenomenon that has to do with refraction called total internal reflection. So before we get to total internal reflection, it's probably a good idea to revisit some of the stuff we looked at on refraction earlier. So I'm going to look mainly at the case when you're going from an optical medium with a high refractive index to one with a lower one. So what happens to a light ray passing from high index to low index? Well, as you might remember, when that's the case, the light ray will be refracted outwards, and you'll end up with an angle of refraction, theta r, that's greater than the angle of incidence, theta I. So that's kind of demonstrated in this image here. We have light rays passing from a material with a very high refractive index, which is diamond, of 2.42, into a material with a lower refractive index, which is air. And you can see as that happens, the light ray is bent outwards as it passes from the diamond into the air. And the refracted angle, theta r, is 38 degrees, which is greater than the incident angle of 15 degrees, as expected. And in each of these little shots here, we're looking at what happens as you increase that angle of incidence. So as the angle of incidence increases, you can see that the angle of refraction gets greater also. Now in this last shot here, you can see that the refracted angle is coming out almost at 90 degrees to the normal there. So it's coming out at 85 degrees. It's pretty damn close to that light ray just skimming along the surface of the diamond. So the question, I guess, here is, what happens if your angle of incidence is greater than 24 degrees, as shown here, and you end up with a ray of light where the angle of refraction is greater than 90 degrees? So it's actually going back into the material. What happens in that case? Well, as you might have been able to guess, what actually happens is the light ray doesn't pass through at all, so there's no refraction. Instead, the light ray reflects back into the material, and we call this total internal reflection, because the material is reflected back inside the material. Sorry, the light ray is reflected back inside the material, and nothing passes through to the other side. So this little video is going to illustrate what's happening here. So up the top here, we've got a light ray traveling through something with a high refractive index, like water, and passing into something with a lower refractive index, like air. Now if we look at this diagram here, you can see that two things are happening when this light ray hits the boundary between water and air. Firstly, we have a very faint line, which shows that some of the light is reflected backwards into the material. Now this will always happen regardless of the situation. There'll always be a small amount of light reflected when it hits the boundary. But you can see here the majority of the light is being refracted through to the other side. Now as I increase the angle of incidence here, you can see that the angle of refraction increases also until we almost get to that 90 degrees point. The light ray appears just to be skimming the surface of the material, and then after that you can see that there's no longer a refracted ray, and instead the light ray just bounces back into the material and obeys the law of reflection we looked at earlier, where the angle of incidence is equal to the angle of refraction. And if we measure that angle, the point at which it goes from refraction to reflection, we can see for this particular material it's about 42, I'd say. And why is that important? Well, in physics we're interested in that angle of incidence where the light ray goes from being refracted to being total internally reflected. We call that the critical angle. So the critical angle is the angle where you go from having refraction to having internal reflection. So for that previous little animation we looked at, the critical angle in that case would have been about 42 degrees, because that's where it went from refracting to reflecting. Now at the critical angle, the angle of refraction will always be exactly equal to 90 degrees. So in this diagram here, I've got as close as possible to the critical angle. So you can see here, theta c, that's the critical angle of incidence. And when you're at the angle of incidence, theta c, the refracted ray will come out at 90 degrees to the normal and will skim along the surface of that material. If your angle of incidence gets any greater than theta c, then there will no longer be refraction and the light ray will be total internally reflected back into the material instead. So what we're going to try and do now is derive a formula that allows us to work out the critical angle. So we're going to start with Snell's law. Ni sine theta I equals Nr sine theta r as before. Except in this case we know that I is going, the incident angle is going to be the critical angle theta c. And we know that if we're at theta c for our angle of incidence, then the angle of refraction will be exactly equal to 90 degrees. So you can see here I've taken that generic expression for Snell's law, and I've replaced it with Ni sine theta c for the critical angle equals Nr sine of 90 for the angle of refraction. Now that's going to simplify to just Ni sine theta c equals Nr. The sine of 90 disappears because we know that the sine of 90 degrees is always equal to 1, and Nr just times by 1 is just Nr. So we've got that. Next step is to rearrange it to get sine theta c by itself. So sine theta c equals Nr over Ni. And then the last step, as with the stuff we looked at with Snell's law problems before, the last step is to then take the inverse sine of both sides, and that gives us a formula that allows us to work out theta c. So the critical angle theta c is equal to the inverse sine of Nr divided by Ni, where Nr is the material the lights should be passing into, and Ni is the material that the light starts in. Now, as with all these problems, you have to be very careful to make sure you label each thing correctly and you don't get them confused. So don't get Ni and Nr confused or you'll get the wrong answer. Okay, so having said that, we're going to skip across to two short examples of how to problem solve with sort of total internal reflection and critical angle type problems. Right, so here's our first example. We're looking at this question and we're trying to find the critical angle for light that's passing from flint glass, which is basically another word for hard glass, which has a refractive index of 1.66, into air. So we start off by drawing and labeling a simple diagram. We have a light ray coming in at the critical angle theta c and being refracted through the other side at an angle of exactly 90 degrees. Now Nr in this case will be 1 because the refractive medium is air, and Ni will be 1.66 because the incident medium is the flint glass. So finish off the diagram, you don't necessarily need to shade them like I have there. And then start the question off by writing down what you know and what you're trying to find. As always, that's a good problem solving strategy for any sort of physics problem. Now I'm going to start my solution here by writing down a general formula for the critical angle. It's slightly different to the one I've given you on the previous slide, but it still works. So sine theta c equals Nr over Ni. Insert your values, do a calculation on the calculator, and then the final step to get the critical angle is to take the inverse sine of that. So critical angle equals inverse sine of 0.602, which gives me a final answer of 37.0 degrees. Now in the second example, we already know what the critical angle is. In this case here, it's diamond passing into air, and we're told that the critical angle is 24.4 degrees. But this time, we want to try to calculate the refractive index of diamond from this information. So in my diagram here, I have a light ray coming in at a critical angle of 24.4 degrees, and then being refracted as it passes through the other side through an angle of 90 degrees, so that light ray is just skimming the surface between the diamond and the air. Now in this case here, the refractive index for air will be 1, and the refractive index for diamond is what I'm trying to find, so I put a question mark there. So I'm writing down what I know and what I'm trying to find, and then from there I'll start off by using the same formula I did in the previous example, except this time I'm going to need to rearrange that to make Ni the subject, because that's what I'm trying to find in this case. So I rearrange it and I get Ni equals Nr sine theta c. Sorry, divided by sine of theta c. From there, I put in the numbers. So sine of theta c will be the sine of 24.4 degrees, because that's the information we were given at the start of the question. And then once I do that, I get a final answer of 2.42 for the refractive index of diamond. Okay, so coming back now to just quickly have a look at a few examples of total internal reflection action. So the first one here is probably the simplest case, and that's when you're looking upwards inside a body of water like the ocean or a pool. Now, when you're looking upwards, you've got light rays that are trying to pass out through the water and into the air. And some of those light rays will hit the surface of the water at greater than the critical angle for a light ray passing from water into air. And in that case there, rather than refracting through, those light rays will be reflected off the top of the water and back into the rest of the water. So basically, at certain angles, the surface of the water will act a little bit like a mirror. And you can see here illustrations of both of those situations. So here you can see that the fish is reflected off the surface of the water, and here the swimmer is. So total internal reflection explains how those rays of light can reflect off the surface of the water. Another example are binoculars. Now you might not notice, but inside binoculars, you have in each eyepiece you have two little triangular glass prisms. And what they're there for is to reflect the light that's coming into the main lenses of the binoculars and bounce them around so they come out through the viewing lenses and into the viewer's eye. Now, the reason we use these glass prisms to reflect light and not a mirror is because it turns out that when light reflects off a mirror, you never get 100% of the light being reflected. Some of that light will always be absorbed by the mirror. Whereas if you get the total internal reflection correct, you get the angle just right, then total internal reflection will always reflect exactly 100% of the light. So it's much, much, much more efficient to reflect light using total internal reflection than it is to use something like a mirror. And it turns out that total internal reflection for glass occurs at angles of incidence greater than 42 degrees. That's the critical angle for some types of glass. So you can see in this diagram here that when the light comes in and hits this surface, if you imagine a little normal line coming out of that surface there would be an angle of incidence of 90 degrees and an angle of reflection of 90 degrees. So basically that light ray is coming into those glass prisms and hitting the surface of them at an angle of 45 degrees. Now, since that angle of incidence, 45 degrees, is greater than the critical angle, the light can't pass from that glass and out of the glass prism into sort of the back part there where I'm moving my mouse. Instead, you get total internal reflection, goes across, hits the same sort of sloped surface on the other side of the prism. Same thing happens again. The angle of incidence is greater than 45 degrees. So refraction is not possible when you get total internal reflection. Bounces off. When it hits this part here, it hits at 90 degrees. So that's fine. It passes straight through. And then the same thing happens in the next prism. And then it comes out through the eyepiece. So these prisms are specially shaped with angles of 45 degrees so that light passing into there experiences total internal reflection and bounces off those sloped surfaces. Okay, now, the big one for total internal reflection, the one, well, not saying that those previous examples weren't good, but this is the really big example of total internal reflection, is the making of what we call optical fibers. So an optical fiber is a very, very, very thin piece of glass fiber, basically like a glass wire. And when I say very thin, I'm talking quite often less than the width of a human hair. So it's a very thin piece of glass surrounded by a material called cladding. And then that cladding is surrounded by a coating that just basically protects the fiber, because as you can imagine, it's quite delicate. Even the cladding itself is not much thicker than the human hair. Now, in this case here, the cladding that surrounds the glass fiber has a lower refractive index than the glass fiber itself does. So here we've got a little cross section. So as you might imagine, when light comes in, it goes into the glass fiber, and when it gets to the edge of the glass fiber, when it gets to the edge of the glass fiber, it's trying to go from material with a higher refractive index into material with a lower refractive index. So it's like the previous examples we'll be looking at. This means that the glass fiber will have a critical angle, and if the light comes in at greater than that critical angle, then it'll be impossible for the light rays to pass from the glass into the cladding, and instead they'll be totally internally reflected. And that's what we've got here. The diagram is a little bit hard to see, but basically we have this thing called an acceptance cone. That's the grey highlighted area here. And any light rays that come in within that acceptance cone will hit the sides of the glass fiber at an angle of incidence that's greater than the critical angle. So basically, they won't pass through the glass fiber into the cladding. Instead, they'll experience total internal reflection and they'll head back into the glass core again. Any light rays outside there will just pass straight through. But any light rays that are inside this grey shaded acceptance cone will be totally internally reflected down the end of the glass fiber. They'll basically just bounce down it until they reach the end, because every time they bounce off, they hit the other side of the core with exactly the same angle of incidence, and the same process repeats. The light rays can't refract through, and instead they're totally internally reflected. And here we have another little illustration of the same thing happening here. Light ray comes in, hits at a large angle of incidence, 75 degrees, greater than the critical angle, bounces off, and the same thing happens at every point along the glass fiber. Now, it turns out in practice that the light ray will sort of bounce along the lengths of the fiber for a certain distance. It won't do that forever. Eventually, it sort of runs out of light, but it is quite far. So for the optical fibers that are used for transmitting information from one point to another, we'll look at that in a second, you can go 100 kilometers basically before the light signal gets too weak and you have to repeat it. So it's pretty. Now, one application of optical fibers is in what we call endoscopes. Now, an endoscope is a device for seeing inside a person's body while they undergo surgery. Quite often used during what's called keyhole surgery, which is when a doctor only opens a very small incision, so the so-called keyhole, in a patient and basically pokes their tools into there. So it's a slightly safer way of doing surgery. You don't have to open up the entire person to do keyhole surgery. Now, obviously, if you're doing keyhole surgery and you only got a very small incision, you can't see inside the person yourself using your eyes. So an endoscope allows the surgeon to see what's happening. Now, it's basically a very, very, very long optical fiber that's passed into the patient's body. So, for example, here in the diagram, you can see that, whoops, too quick. In this diagram here, you can see that the endoscope has been inserted into the patient's stomach via the esophagus. So light is shone down this optical fiber. That's used to illuminate the inside of whatever you're looking at. So in this case, illuminate the inside of the stomach. And then the light that's reflected back enters the endoscope and travels down it via total internal reflection, because it's basically just an optical fiber, up to the other end, where there'll either be like a little viewing port, or possibly it just goes directly to a TV monitor. So by using the endoscope, the surgeon can see what's happening inside the patient as they operate on them. So here we've just got a quick little video showing an endoscope actually being used. This is an endoscope being used to have a look inside someone's esophagus and their stomach. Now, as far as I can tell, it's just a mess. I have no idea which part is the stomach and which part is the esophagus. But you can see quite clearly how the endoscope is sending light into there, quite a bit of it, and then that light is being reflected backwards and then picked up by the optical fiber that makes up the endoscope and reflected back through that process that we call total internal reflection. And then our last application we'll look at here, again, it's using optical fibers. This is probably the most common way of using optical fibers, the most widespread application, and that's for high-speed telecommunications. Basically for sending telephone and internet signals between countries or between cities. So as you can see here, this is a typical sort of optical fiber. It's actually a bundle made up of many, many, many smaller optical fibers. Now, the reason we use optical fibers for doing telecommunication is not so much that that signals travel faster down them than they do with regular copper cables and electricity. It's that light rays can have a higher bandwidth than electrical signals down a copper wire can. And bandwidth is basically how many different signals can be on the wire at once. So with copper, you can have many different signals traveling down the wire at once, but with light traveling down fiber optic cables, you can have many, many, many times more, which allows you to carry more data more conversations, high-speed internet, all that kind of stuff. So it's about the higher bandwidth. That's the reason we like using fiber optics instead of copper cables. Now, how do you transmit information using light? Well, we won't go into huge details about this because it's quite complicated, but basically you just pulse the light. If you want to think of a really oversimplified way of doing it, then when we transmit data digitally, it's either ones or zeros. You imagine a 1 as being light on and the 0 as being light off. So every time you want to transmit a 1, you pulse the light on. Every time you want to transmit a 0, you pulse the light off. That's a very, very, very gross oversimplification, but it's basically a rough idea of how it works. Okay, so that gave you a bit of a rough idea of total internal reflection, how it works, how to calculate the critical angle, and some of the more common applications of total internal reflection. Now, that sort of completes our section on refraction and its applications. Next time we're going to head on and look at color and how the different colors in the rainbow are created from white light and how our eyes perceive color and how you can make some colors from other primary colors added together. So we'll look at all that stuff in the next video. Okay, until then, I'm out.